Hey y'all, I hope y'all are ready to keep moving on. All right, so we have been doing our walking directions lab for over a week now. So hopefully you have gotten a little insight into what I told you we were starting on the very first day, and that was one-dimensional motion. Okay, so that's motion in one dimension. So today we're really jumping into actual physics. So whenever we talk about one-dimensional motion, that means that we are only moving in one dimension. That doesn't mean that we're just moving in one direction. That means that we're only moving in one dimension. So we are either moving horizontally or we're moving vertically. We are not moving horizontally and vertically at the same time. So that would be two-dimensional motion, which we will get into, just not right now. So again, motion in one dimension means that I am either moving horizontally or I'm moving vertically. All right, so motion, whenever we start talking about motion, is going to fall under the branch of physics that we call mechanics. All right, this was in Newtonian physics, and this was one of the branches that we learned about a couple of weeks ago. All right, so mechanics is actually split into two separate branches in and of itself. The first one being kinematics. If you are watching this in the classroom, then you should see the posters that have our kinematics equations on them. All right, so this is what we're going to be working on or working with pretty much for all of first semester. All right, so all we are doing in kinematics is we are just describing the motion of objects. All right, we are just describing why is it, or like if it changes this much distance in this much time, what is its velocity? All right, things like that. The second part of mechanics is something called dynamics, and that's what we are really going to be digging deep into during second semester, and that deals with the effects of the forces that are causing the motion. So why is the object slowing down? Why is the object speeding up? Why is the object changing direction? All right, so that is what we are really starting to look at now. All right, so whenever we look at motion, remember this is all about describing motion. All we are doing is looking at the change of an object's position. The change of an object's position, the biggest part comes right here, relative to some reference point. Relative to some reference point. All right, now that reference point is going to play into big things later on. All right, and especially this, you always have to have a reference point. So it's your reference point that's going to tell you, if you're moving to the right or to the left or something like that, okay? So obviously, objects that are at rest are not moving, so there is no motion. That's, you will see that again. So just know that objects that are at rest are not in motion, all right? They do not have any speed, no velocity, anything like that. So whenever we describe this motion, we have to have that reference point. All right, the most basic information that we need is the object's position and its time. We have been dealing with this for the entire last week with our motion graphs. All right, we have been looking at how our people have changed their positions over time. All right, now that reference point is huge. Okay, so say you're driving on the interstate, or say you're riding in the back seat on the interstate. All right, you're in the car that is moving, obviously, but if you look out of the window, like you've probably done a million times as a kid, maybe before you got phones, all of that. If you look out of the window, what are your eyes following? What are your eyes following as you look out the window, as you're driving down the road? Normally, your eyes are following the trees. So from your reference point, if you are the reference point inside the car, it feels like you are not moving, but all the trees, all the signs, everything else outside of the car is moving, but you're standing still. Now, what if you were standing on the side of the interstate? Okay, you look behind you, behind those trees, those are definitely not moving. You're not moving. And then you see a car pass by, it looks like the person in the car and the car are the ones moving. So it all just depends on what your reference point is. And that's going to get into relative motion. Whenever we get into that, we're mainly going to focus on that second semester. Just know what a reference point is and that it is super important. All right, now we have already talked about this. Whenever we talk about measuring motion, we have two types of quantities. We have two different types of quantities in all of physics. I did an extra loop, it's fine. All right, so we have scalar quantities and then we have vector quantities. I told you that these will follow us for the rest of the school year. So you have to know the difference between these. All right, a scalar quantity will only have magnitude. Okay, so it's only going to have that numerical value. It has no direction. It doesn't care about direction. It just has the numerical value. Vector quantities, on the other hand, have both magnitude and direction. Their direction does count. It does come into play. All right, but always remember, we always include our units with these. Always include our units. Okay, so a scalar quantity just has magnitude. Vector quantities have both magnitude and direction. All right, so let's look at the first of our two scalar and vector quantities. All right, we're going to have distance versus displacement. We have distance versus displacement. Okay, that's what we're looking at today. All right, so distance we have been using pretty much since the beginning of the school year. We have our lowercase d, that's the symbol that we use for distance, and it's just how far an object travels. Distance is a scalar quantity. Distance is a scalar quantity. It does not depend on direction. It does not care what direction they were going and when. All right, so your distance is going to look at the entire path the object or the person takes. All right, so say we have this cute little ant who is on our ruler. All right, our ant starts at 0 and then marches to the right to the 3. This is a centimeter ruler. So what distance did he travel? 3 centimeters. All right, his distance was 3 centimeters. Easy peasy. Okay, so we're looking at the path whenever we talk about distance. Okay, now the same ant, look, now he is starting at 3 and moving to the left, and he's going to that 0. So what distance did the ant travel now? Because we know distance does not depend on direction, we just have 3 centimeters. Our ant just traveled 3 centimeters. So does his direction change the answer from this one to this one? No, it does not, because distance does not take your direction into account. Now let's look at this one. Okay, this was just one single path that he took. All right, now we have the same ant. Now he's starting at 0, traveling to 5, but then, oh, he forgot something, and he's going to turn around and go to 3 centimeters. So again, distance is looking at the entire path, So we would take the 5 centimeters that he traveled to the right and then add that to the 3 centimeters that he traveled to the left. It does not take into account the direction that he went. It just takes every single step that he made into account. All right, so his distance was 7 centimeters. 7 centimeters, because he went from 0 to 5, that's 5, and then from 5 to 3, that's 2. So we have 5 plus 2, which gives us 7 centimeters. So again, your distance, because it is scalar, does not depend on its direction. It is looking at the object's entire path. All right, now displacement, on the other hand, is a vector quantity. It is a vector quantity. All right, so we need to remember vector quantities have both magnitude and direction. So this does take the direction into account. All right, so displacement is an object's change in position. So I want to break that down. A change in. We have seen that before. We have seen that terminology before. A change in. Hopefully everybody is thinking of the symbol delta. All right, delta anything just means a change in. Well, remember, we are changing position either horizontally. Well, if we're looking at a graph, the horizontal axis is our x-axis, or it could be changing position vertically, and that is on the y-axis. All right, so position could be horizontal or vertical, and if we have a change in position, that is going to be either delta x or delta y. All right, so everything that we're going to be doing, especially this first little part, is going to be horizontal. So our displacement is mostly going to be symbolized with delta x. That is a change in position. That's a change in horizontal position. I just want you to know that this could also be delta y, which is a change in vertical position. All right, so the only two things that displacement takes into account is its starting point, so its starting position, and its ending point, or its final position. All right, so if we have our displacement, we have our first big equation for this, and that's going to be our displacement is equal to our final position minus our initial position. This could also say delta y is equal to y final minus y initial. So x and y are both positions, but remember, the only two things that displacement takes into account is your final position and your initial position. Unlike distance, distance takes your entire path into account, and displacement only takes your initial position and your final position into account. Okay, now again, with displacement being a vector quantity, that means that you have to have a direction. So we've talked about north, south, east, and west. We're going to talk about angles later on. We're going to talk about cardinal direction. Well, those are cardinal directions, are the north, south, east, and west. But mainly, I want you to use positive and negative. Those are going to be our numerical directions. All right, so once again, our distance is a scalar quantity, displacement is a vector quantity. So this kind of shows you the difference, okay? So our distance is that purple line. All right, the distance is the entire path taken. All right, that's because distance is scalar and it does not care about the directions that it took, the direction that the person or the object went. It takes into account every single movement that was made. Your displacement, on the other hand, only looks at your initial position and your final position and is comparing those. Okay, so again, distance is scalar, only magnitude, displacement is vector, magnitude, and direction. All right, so if we're looking at the same ant, this same exact ant that we looked at earlier, all right, his starting position is 0. All right, that's his initial position, and his final position is 3 centimeters to the right, which is going to be in the positive direction. All right, so if we wanted to figure out its displacement, we have our equation. Our delta x is equal to our final position minus our initial position. So that is a positive 3, it's 3 to the right, minus 0. Well, what is positive 3 minus 0? That's going to be plus 3 centimeters. So you could have also said 3 centimeters to the right. Okay, either one of those are correct. Either one of those are correct. All right, we have to have that direction. That positive is what gives us that direction. If you wrote 3 centimeters to the right, it's the right that gives us that direction. All right, now the second one. All right, so the ant this time starts at 3. Okay, so that is now its initial position, and then it ends at 0, which is its final position. Well, if I want to know the displacement, I know delta anything is final minus initial, so we have our final position minus our initial position. So final is 0 minus a positive 3, because it's 3 to the right. Well, 0 minus anything is going to give us a what? It's going to be a negative number. So our displacement is negative 3 centimeters, or 3 centimeters to the left. That's where it was traveling, was to the left. All right, so again, we have to have those directions for these. Now, notice that the numerical value for both of these, for distance and displacement, have been the same. Okay, that can happen whenever we only have one single motion being made. All right, so for this first one, all we added was that plus because it was moving to the right. For the second one, we added that negative because it was moving to the left, and that was the only difference. But that was only because we had one single motion. All right, so look at this one. So remember that the ant starts at 0. So that's his initial position. He travels to 5 centimeters, and then he goes to 3 centimeters. So our final position is that positive 3 centimeters. So if I'm looking for my position, remember my distance is looking at the entire path. So I would add every single centimeter that he traveled up, which gave us 7. But whenever I'm looking for displacement, the only 2 points that matter are its final position and its initial position. So we subtract those. So we have our positive 3 minus 0. Okay, so our final position is our positive 3 because it's 3 to the right, and our initial position is 0. So we have 3 minus 0, which gives us positive 3 centimeters. Okay, so our displacement is positive 3. So notice the difference. So with the other two, the distance and the displacement were the same. We just had directions added to them. But this one, because it was 2 different motions, these two are not going to be the same. Okay. All right, now look at this one. A lot of people get this one confused. So we have a track. So this is just like our track outside. So we have an athlete who starts at that little red dot, and they run around the 100-meter long track 3 times. So they go 1, 2, and then 3. Okay, so they run around the track 3 different times. I want to know what is the athlete's distance and its displacement. All right, well, distance takes into account every single motion that the athlete made. So if he ran around that 100-meter track three times, what is 3 times 100? That is 300 meters. We do not think about the direction that he went. We're just looking at every single step that he took, which is just 300 meters. Now, the 2 different things that displacement depends on is your initial position and your final position. Well, what do you notice about the initial position and the final position that the athlete started and ended on? They're the same, right? So if they are the same point, so if you end where you start, then your displacement will always be 0. Your displacement will always be 0 because your final position and your initial position are the exact same. Okay? Now, last thing, I want you to look at this graph. So we have a position versus time graph. This is the same thing that we have lining our boards all around class right now. Those are all position versus time graphs, distance versus time graphs, displacement versus time graphs. You can call them all the same thing. They all mean the same. We're just looking at a change in position. All right, I want you to answer these 4 questions. What is the object's position at 1 minute? What is the object's position at 2 minutes? What is its displacement between 1 and 5 minutes? And then describe the motion of this object. So I want you to answer those 4 questions, and I want you to come see me tomorrow. We'll answer them and go over them. All right? If you have any questions, as always, let me know.